Imagine looking up at the night sky. Each star is a sun, a distant beacon of light. For generations, we have stared into that darkness and asked the biggest questions. Where did all this come from? How did it all begin? For a long time, we thought we had a pretty good story, a scientific origin myth for our cosmos. We called it the Big Bang. It's a story of a singular, explosive moment of creation from nothing. But what if that story is just one chapter in a much, much longer book? What if the beginning we thought we knew was not the beginning at all? Science is a journey of discovery, and sometimes, the most exciting discoveries are the ones that force us to rethink everything. The universe is a mysterious place. It doesn't give up its secrets easily. We build incredible tools, like giant telescopes that can see across billions of light years, to piece together the puzzle. With every new image, with every new piece of data, we fill in another part of the cosmic picture. For decades, that picture seemed to show a universe that started small and hot, and has been expanding and cooling ever since. This has been the bedrock of modern cosmology, our guiding star in understanding the cosmos. It's a powerful and elegant idea, one that has explained so much about the world we see around us. But science thrives on challenge, on questions that poke holes in our most cherished theories. Recently, our most powerful eyes on the sky have started to show us things that are unexpected. They have found objects that seem too old, too mature, to exist so early in the cosmic timeline. It's like finding a fully grown oak tree in a photograph taken just one day after the first seed was supposedly planted. These discoveries don't necessarily mean our old story is completely wrong, but they do suggest it might be incomplete. They whisper of a history before the beginning, a past that we are only just starting to glimpse. The universe might be older, stranger, and more complex than we ever dared to imagine. This is the thrill of scientific exploration. It is not about having all the answers. It is about the courage to ask new questions, especially when the evidence demands it. It's about being humble enough to admit that our grandest theories might just be stepping stones to an even grander truth. The story of the universe's origin is not a closed book. In fact, a new chapter may be opening right now. So, let's venture into this new, unfolding narrative and explore the possibility that our cosmos is part of something eternal, a never-ending cycle of birth, death, and rebirth. To understand where we might be going, we first need to understand the story we've been telling for the last century. This is the story of the Big Bang. Picture this. About 13.8 billion years ago, everything you see and everything you don't was compressed into a point of unimaginable density and heat. It was smaller than a single atom. There was no space, no time as we know it. Then, in an instant, it all began to expand. This wasn't an explosion in space, but an explosion of space itself. The universe was born, and it has been expanding outwards ever since, like the surface of a balloon being inflated. From this fiery start, the fundamental forces of nature emerged. As the universe expanded, it cooled. The raw energy began to congeal into the first elementary particles. Think of it like steam cooling and condensing into water droplets. Over hundreds of thousands of years, these particles came together to form the first simple atoms, mostly hydrogen and helium. The cosmos was filled with a hot, dense, glowing fog. There were no stars, no galaxies, just this primordial soup of matter and radiation, expanding and cooling in the dark. It's a dramatic and powerful story, supported by decades of careful observation and mathematical theory. One of the most powerful pieces of evidence for this story is a faint glow that fills the entire sky. It's called the cosmic microwave background, or CMB. This is the afterglow of the Big Bang itself, the leftover heat from that initial creation event. Discovered by accident in the 1960s, this ancient light has traveled across the entire observable universe for 13.8 billion years to reach us. When our telescopes look at the CMB, they are looking at a baby picture of the universe. It shows us what the cosmos looked like when it was only about 380,000 years old, a snapshot of the moment when it first became transparent to light. This standard model has been incredibly successful. It predicted the existence of the CMB. It explains why the universe is still expanding today, with distant galaxies rushing away from us in all directions. It even accounts for the abundance of the light elements, like hydrogen and helium, that we see in the cosmos. The Big Bang theory became the champion, the undisputed narrative of our cosmic origins. It gave us a timeline, a starting point,
and a framework for understanding everything that followed. For a while, it seemed like we had the fundamental story right. But the universe, it turns out, always has more surprises in store.
Our newest and most powerful space telescopes, like the James Webb Space Telescope, are time machines. Because light takes time to travel, when we look at very distant objects, we are seeing them as they were in the distant past. We are looking back towards the dawn of cosmic time. These telescopes were built to see the very first stars and galaxies forming after the Big Bang. We expected to find small, clumpy, infant galaxies, the first tentative structures just beginning to take shape. But that's not entirely what we found. Instead, we found some ghosts in the cosmic machine. Objects that shouldn't be there. Imagine peering into the universe's nursery and finding teenagers. That's the kind of surprise we've been getting. Telescopes have spotted galaxies that are astonishingly large, well-structured, and mature, at a time when we thought only the first baby galaxies should exist. These are massive spiral galaxies that look surprisingly like our own Milky Way, but they appear at a point in history just a few 100 million years after the Big Bang. According to our models, there simply shouldn't have been enough time for them to grow so big and organized. It's a profound cosmic puzzle. It's not just the galaxies. We've also found supermassive black holes lurking at the centers of these early galaxies. These are not your average black holes. They are monsters, billions of times more massive than our sun. The problem is, black holes grow by swallowing matter, gas, dust, and stars. For a black hole to become a supermassive one, it needs a lot of time and a lot of food. Finding these cosmic titans so early in the universe is like finding a 100-story skyscraper built in a week. The standard timeline of cosmic evolution just doesn't seem to give them enough time to get that big, that fast. These aren't just minor anomalies that can be easily explained away. They represent a fundamental challenge to our understanding of cosmic evolution. These impossible early objects are real. We can see them. Their light has traveled billions of years to reach us, carrying a message from the deep past. And that message is, things might have been happening long before we thought they could. The cosmic clock might have started ticking much earlier than the Big Bang model suggests. These ancient ghosts are forcing us to confront the possibility that our origin story needs a prequel. When observations clash with theory, that's when science gets really exciting. It's a signal that we're on the verge of a breakthrough. These timeline problems, the two old galaxies, the two big black holes, are not just headaches for astronomers. They are clues. They tell us that our neat, linear story of the Big Bang might be missing a crucial piece. The universe we are observing doesn't quite match the universe our models have predicted. This discrepancy is a creative force, pushing us to explore new, and sometimes radical, ideas about the nature of reality and the origin of everything. Think of it like being a detective at a crime scene. You have a theory of what happened, but then you find a piece of evidence that just doesn't fit. You find a footprint that doesn't match any of your suspects. You don't just ignore the footprint, you revise your theory. In cosmology, the impossible galaxies and black holes are our mysterious footprints. They force us to ask, could our assumptions be wrong? Could the universe have had more time to build these complex structures? Did something happen before the Big Bang that gave the cosmos a head start? This challenge to the standard model opens up a universe of possibilities. It pushes physicists and astronomers back to the drawing board. They must now try to figure out how these mature structures could form so quickly. Perhaps the seeds of these giant galaxies were much larger than we thought. Maybe the processes of star formation and black hole growth were far more efficient in the early universe than they are today. Or maybe, just maybe, the universe didn't start from a single point 13.8 billion years ago. Maybe that event was not a beginning, but a transition. This is how scientific progress works. It's a constant dialogue between theory and observation. For a long time, the dialogue was harmonious. The Big Bang theory would make a prediction, and our telescopes would go out and confirm it. But now, our telescopes are talking back. They are showing us a cosmos that is richer and more complex than our theories allowed for. This isn't a failure of science, it is its greatest triumph. It shows we are capable of building instruments powerful enough to question our own deepest assumptions and set us on a path toward a new, more complete understanding of the cosmos. Faced with these timeline paradoxes, scientists are exploring a fascinating and, honestly, mind-bending alternative to the Big Bang. It's called the Big Bounce. This idea suggests that our universe is part of an endless cycle of expansion and contraction. Instead of a single beginning from an infinitely dense point, the Big Bounce theory proposes that our universe actually emerged from the collapse of a previous one. Imagine a cosmos that existed before ours, filled with its own stars, galaxies, and perhaps even its own life. After trillions of years, its expansion slowed, reversed, and it began to collapse back in on itself. In this scenario, the universe didn't collapse into a singularity, that point of infinite density, which, breaks the laws of physics. Instead, as it got incredibly dense and hot, a new kind of physics took over. Some scientists propose that quantum gravity, a theory we're still working pretty hard to understand, would create a repulsive force that would halt the collapse. This would cause the universe to bounce. The immense energy of the collapse would be redirected, triggering a new phase of rapid expansion. That explosive expansion would look, from our perspective, exactly like a Big Bang. So, the event we call the Big Bang was not a moment of creation from nothing, but a moment of transition. It was the point where a contracting universe bounced and became our expanding one. This elegant idea solves some of the most difficult problems in cosmology. For one, it removes the need for a singularity, that mathematical point where our theories just break down. The universe never reaches an infinite density, so the laws of physics always apply. It provides a natural physical mechanism for the beginning of our cosmic expansion. The Big Bounce kind of reimagines our place in cosmic history. We are not living in the first and only universe. Instead, we could be inhabitants of just one iteration in an eternal sequence of universes. The cosmos becomes a phoenix, perpetually reborn from the ashes of its former self. This isn't just a philosophical fancy. It's a serious scientific hypothesis that makes testable predictions. It suggests that the clues to a previous universe might still be hidden within our own, just waiting to be discovered. It transforms the question from, how did the universe begin, to what happened in the universe before ours? To grasp the idea of a Big Bounce, let's use an analogy from our own world. Think of a computer. Sometimes a program crashes, or the whole system freezes up. What do? You reboot it. You turn it off and on again. The computer doesn't disappear and come back from nothing. The hardware is still there. When you restart it, the operating system reloads, and it starts fresh. The old crashed state is gone, but the fundamental system endures. The Big Bounce is like a grand cosmic reboot. The universe doesn't start from scratch, it resets. In this analogy, the previous universe is like the computer running a complex set of programs for a very long time. Eventually, it reaches a state where it can't continue expanding. It collapses. The Big Crunch is the shutdown process. The Big Bounce itself is the moment you hit the power button again. The fundamental hardware of the cosmos, the underlying laws of physics, persists through the bounce. What emerges is a new, rebooted universe, with its energy and matter reset into a hot, dense state, ready to begin expanding and evolving all over again. The Big Bang becomes the boot-up screen of our current cosmic operating system. This concept helps to explain those two old galaxies and black holes. They might be relics. In a computer reboot, sometimes fragments of old data can survive the process, leading to glitches or unexpected files in the new session. Similarly, if the Big Bounce is real, perhaps not everything from the previous universe was completely erased. Maybe the immense gravitational structures, like the supermassive black holes, were able to survive the bounce in some form. They would then act as seeds in our new universe, allowing galaxies to form around them much faster than they could on their own. Thinking of the universe as a piece of software that can be run again and again also changes how we view its fundamental laws. Are these laws permanent, like the computer's hardware? Or are they like settings that can be slightly different with each reboot? Could the physics of the next universe be different from our own? This analogy helps us frame the biggest questions in cosmology in a new light. We are no longer just studying the birth of our universe, but trying to understand the operating manual for a system that might be eternal, a system that has run before and will run again. If a universe existed before ours, is there any way we could prove it? Could any evidence have survived the cataclysmic bounce? Some scientists believe the answer is yes. They are searching for what could be called cosmic fossils, imprints left over from the pre-bounce cosmos, hidden within our own. These wouldn't be dinosaur bones or ancient ruins, but subtle patterns and anomalies in the fabric of space and time. Finding such a fossil would be one of the greatest discoveries in the history of science, confirming that we are part of something much grander and older than we knew. One place to look for these fossils is in the cosmic microwave background. As we've discussed, the CMB is a baby picture of our universe. It's incredibly uniform, but not perfectly so. It has tiny variations in temperature, minuscule hot and cold spots, that eventually grew into the galaxies and cosmic voids we see today. The standard Big Bang model explains these variations as random quantum fluctuations from the earliest moments of time. But the Big Bounce theory offers another possibility. What if some of these patterns are not random at all? Imagine a vast ocean beach at low tide. The sand is mostly smooth, but you can see faint ripples left by the waves of a previous high tide. In the same way, some Big Bounce models predict that the gravitational forces from the collapsing previous universe could have left a distinct, non-random pattern imprinted on the fabric of our new universe. These imprints would appear as specific anomalies in the temperature map of the CMB. Scientists are meticulously scanning the CMB data, looking for these telltale signs, these faint ripples from a cosmic tide that receded long before our time began. Another type of cosmic fossil could be related to gravity itself. The Big Bounce theory is rooted in quantum gravity, the yet-to-be-completed theory that unites Einstein's general relativity with quantum mechanics. This theory predicts the existence of gravitational waves, which are ripples in space-time. Just as the Big Bang is thought to have produced a background of gravitational waves, a big bounce would have done the same. The specific signature of these waves from a bouncing universe could be different from that of a universe born from a singularity. Our future gravitational wave observatories might one day be able to detect this ancient echo, the sound of a universe being reborn. For decades, we have spoken of the cosmic microwave background as the first light of the universe. We called it that because it represents the moment, 380,000 years after the Big Bang, when the cosmos cooled enough to become transparent. Before that, the universe was an opaque, glowing fog, and light could not travel freely. So, the CMB is the oldest light we can possibly see. It has been our ultimate boundary, the wall at the beginning of cosmic time. But the Big Bounce theory asks us to reframe this poetic concept. What if it wasn't the first light at all? In a cyclical universe, the CMB is not the light of creation. It is the light of a new morning after a long, dark night. It marks the moment our current cosmic day began, when the fog of the bounce finally cleared. The energy that makes up the CMB's glow wouldn't have come from a singular point of creation, but from the recycled, re-energized matter and energy of the universe that came before. The first light is therefore transformed into the next light. It's the flashbulb going off as our current cosmic chapter started, but it doesn't preclude the existence of previous chapters. This shift in perspective is profound. It means that the wall at the beginning of time might not be a wall at all, but a curtain, and behind that curtain lies another, older cosmos. Our telescopes, by looking at the CMB, are staring at that curtain. The search for cosmic fossils is an attempt to find a tear in it, a tiny glimpse of what lies beyond. The Big Bang singularity was an absolute beginning. It was a point beyond which we could not ask what came before, because the very concept of before didn't exist. But a big bounce is not an absolute beginning. It's a transition point. Therefore, the question what came before the Big Bang is no longer a nonsensical one. It becomes the most important question we can ask. The Big Bounce theory gives us a scientific framework to pursue that question. It turns an unbreachable barrier into a new frontier for exploration. The beginning of our universe is no longer a mystical event outside the laws of physics, but a physical process that can, in principle, be understood. The oldest light in our sky might not be an echo of a birth, but an echo of a rebirth. So, what does it mean for us, for humanity, if we live in a universe that reboots? What does it mean if the cosmos is not a one-time event, but an endless cycle of birth, death, and renewal? On one hand, it can feel like it diminishes our significance. Our 13.8 billion-year-old universe, which already felt unimaginably vast and ancient, suddenly becomes just one of perhaps an infinite number of cosmic episodes. Our existence is a fleeting moment, not just in one cosmic lifetime, but in an eternal succession of them. The story of the cosmos did not begin with us, and it will not end with us. But I see it differently. I think it makes our existence even more wondrous. It connects us to something truly eternal. If the universe recycles, then the very atoms that make up your body, the carbon, the oxygen, the iron, were not necessarily forged in this universe alone. They may have existed in different forms in a previous cosmos. They may have been part of ancient stars, distant galaxies, and perhaps even other forms of life in a universe that has long since vanished. You are, in a very real sense, a child of eternity, built from the stardust of not one, but countless universes. This idea invites us to look up at the night sky with a new sense of wonder. When you see a star, you are not just seeing a ball of gas burning billions of miles away. You are seeing a part of a grand cosmic ecosystem. That star will one day die, and its elements will be scattered into space to form new stars and new planets. And perhaps, trillions of years from now, the entire universe will collapse and bounce, and those same elements will be recycled to participate in the birth of a new cosmos. The universe is the ultimate recycler. Nothing is ever truly lost. This cosmic perspective offers a profound sense of connection. We are not isolated beings on a lonely planet in a one-off universe. We are temporary custodians of matter and energy that are as old as time itself. We are a part of a process that may have no beginning and no end. So the next time you look at the stars, don't just see them as distant points of light. See them as evidence of this incredible, never-ending story. Feel the awe of being a conscious part of a universe that is forever remaking itself. And wonder, what secrets will we uncover in our brief, shining moment in the cosmic day?